Floods, while often sudden and unpredictable, are the result of complex interactions between natural processes and human activities. To fully grasp the nature of floods, it is essential to understand the diverse causes and types that define these devastating events. Floods can strike anywhere in the world, from low-lying coastal areas to mountainous regions, and can vary in their intensity, duration, and impact. Floods occur when water levels rise beyond the capacity of rivers, lakes, canals, or seas, inundating normally dry areas. The primary causes of floods can be broadly classified into natural and anthropogenic, human-induced, factors. Heavy rainfall, one of the most common causes of floods, is intense, prolonged rainfall. When a region experiences a downpour that exceeds the drainage capacity of the soil and river systems, water begins to accumulate, leading to floods. Factors such as tropical cyclones, monsoon rains, or atmospheric river storms can trigger heavy rainfall that leads to riverine flooding. In mountainous areas, this can cause flash floods as water quickly runs down steep slopes. Snowmelt. In regions with significant snowfall, the onset of warmer temperatures in spring leads to rapid snowmelt, which can overwhelm rivers and streams. The speed and volume of snowmelt are critical. A sudden rise in temperature can cause a rapid influx of water into river systems, leading to flooding in downstream areas. This is particularly common in mountainous regions or areas with a seasonal snowpack. Storm surges and tidal flooding. Coastal flooding can occur when strong winds from tropical storms, cyclones, or hurricanes push ocean water onto land. This phenomenon, known as a storm surge, raises sea levels temporarily and can inundate coastal cities and low-lying areas. Combined with high tides, storm surges can cause severe flooding over large areas, especially when the coastline is flat or there are no natural barriers to absorb the impact. Overflowing rivers. When rivers receive more water from rain or melting snow than they can contain, they overflow their banks, causing riverine or fluvial flooding. This type of flooding is common in river basins, especially during rainy seasons or after long periods of heavy rainfall. In areas where rivers meet their floodplains, the risk of flooding is particularly high. Natural barriers and topography. The shape of the land plays a significant role in determining where and how floods occur. Valleys, low-lying plains, and areas near large bodies of water are more prone to flooding. In addition, geological events like landslides or earthquakes can create natural dams or redirect water flows, leading to flooding in areas that are not usually at risk. Urbanization and land use changes. Human activities have significantly altered the natural landscape, often increasing the risk of flooding. Urbanization replaces permeable surfaces like soil and vegetation with impermeable materials like concrete and asphalt, which reduce the ground's ability to absorb water. This leads to increased runoff and a higher likelihood of surface or pluvial flooding during heavy rains. Moreover, deforestation, mining, and land reclamation activities disrupt natural water channels, exacerbating the risk of floods. Deforestation and wetland destruction. Forests and wetlands act as natural sponges, absorbing rainwater and reducing the speed and volume of water entering river systems. The removal of vegetation due to deforestation or the draining of wetlands for agriculture and development reduces this natural absorption capacity, leading to an increased risk of floods. Without these natural barriers, water flows more quickly into rivers, increasing the likelihood of riverine flooding. Climate change. Climate change is altering weather patterns globally, leading to more frequent and intense rainstorms, rising sea levels, and changing snowmelt patterns. These changes contribute to the increasing frequency and severity of floods. Warmer temperatures cause more evaporation, which in turn leads to more intense precipitation events. At the same time, rising sea levels due to melting polar ice and thermal expansion increase the risk of coastal flooding and storm surges. Dam failure and poor water management. The construction and management of dams, levees, and other water control structures can inadvertently increase flood risks. If these structures are poorly designed, inadequately maintained, or overwhelmed by unexpected water volumes, they can fail catastrophically, releasing massive amounts of water downstream. Moreover, the mismanagement of water resources, such as excessive withdrawal from rivers for irrigation or the neglect of drainage systems, can lead to localized flooding. Floods can manifest in several different forms, each with unique characteristics, causes, and impacts. Understanding the different types of floods is crucial for effective preparedness and response. Riverine floods occur when water levels in rivers, streams, or lakes exceed their banks, inundating surrounding areas. These floods are often caused by prolonged rainfall, snowmelt, or a combination of both. Riverine floods can last for several days or even weeks, affecting vast areas and causing extensive damage to infrastructure, agriculture, and homes. They are most common in large river basins and floodplains. Flash floods are characterized by their sudden onset and rapid rise. They occur when intense rainfall overwhelms drainage systems or causes rivers and streams to overflow within a short period, often within minutes or hours. Flash floods are particularly dangerous because they come with little to no warning and have strong, fast-moving waters capable of sweeping away vehicles, buildings, and people. They are common in hilly or mountainous regions, where water can quickly accumulate and descend with force. Coastal floods occur when high tides, storm surges, or tsunamis push seawater onto land, inundating coastal areas. These floods can result from tropical storms, cyclones, or other meteorological events. Coastal flooding can be exacerbated by rising sea levels and can cause significant damage to coastal cities, infrastructure, and ecosystems. In addition to immediate damage, saltwater intrusion can contaminate freshwater resources and soil, making recovery more challenging. Pluvial floods, also known as surface water floods, occur when heavy rainfall saturates the ground or overwhelms urban drainage systems. Unlike riverine floods, pluvial floods do not require a nearby water body to overflow. Instead, they occur when the ground cannot absorb the excess water, causing water to pool in low-lying areas, streets, and basements. Pluvial floods are common in urban areas, where impermeable surfaces like roads and buildings prevent water from being absorbed into the ground. Ice jam floods occur in cold regions where frozen rivers and streams experience a thaw. As temperatures rise, chunks of ice break apart and float downstream. When these ice chunks accumulate and form a dam-like blockage, the water behind the ice jam can rise rapidly, causing flooding upstream. When the ice dam eventually breaks, it can release a sudden surge of water downstream, creating a second wave of flooding. Floods are not one-size-fits-all events. They vary significantly based on regional factors such as climate, geography, and human development. For example, tropical regions are more susceptible to flash floods due to intense seasonal rainfall, while temperate regions may experience riverine floods from snowmelt and prolonged rains. Coastal areas face a higher risk of storm surges and tidal flooding, while urban areas are particularly prone to surface water floods due to their impermeable surfaces. Local human activities, such as deforestation, urban sprawl, and the construction of dams, further complicate this interplay. Understanding these regional variations is crucial for developing targeted flood management strategies that address the unique characteristics and vulnerabilities of each area. By understanding the genesis of floods, from their natural causes to human-induced factors and diverse types, we can better prepare for and mitigate their impact. Awareness of these elements helps in the development of early warning systems, community education, and infrastructure planning that reduce the risks associated with floods. The ability to predict and respond effectively to different types of floods is critical for safeguarding lives, property, and ecosystems in an increasingly unpredictable world. Understanding the origins of floods is the first step in a broader effort to build resilience against these natural disasters. It requires a concerted effort by scientists, policymakers, and communities to learn from past events, adapt to current challenges, and prepare for future uncertainties. Floods, in their many forms, are among the most destructive natural disasters on Earth. They strike with sudden force, leaving behind a trail of destruction that affects every aspect of life. From claiming lives and displacing populations to damaging infrastructure and disrupting economies, floods inflict widespread devastation. Floods are notorious for their potential to cause significant loss of life. The sudden rise of water can trap people in their homes, sweep away vehicles, and destroy entire communities in minutes. Flash floods, in particular, pose a high risk due to their rapid onset, catching people off guard with little to no warning. The powerful currents can carry away adults and children alike, and the debris carried by floodwaters can cause severe injuries. Beyond physical harm, floods often result in mass displacement. Floodwaters force families to flee their homes, sometimes permanently, leading to a significant number of internally displaced persons, IDPs. temporary shelters can become overcrowded, lacking essential services and adequate sanitation, which further exacerbates the hardships faced by displaced populations. The trauma of losing loved ones, homes, and livelihoods can have long-lasting psychological effects, including post-traumatic stress disorder, PTSD, depression, and anxiety. Floods also create a breeding ground for waterborne diseases, such as cholera, typhoid, and dysentery, as contaminated water sources become the primary source of drinking water. The stagnant floodwaters can also lead to outbreaks of vector-borne diseases like malaria and dengue fever, as they provide ideal conditions for mosquitoes and other disease-carrying insects to breed. Additionally, floodwaters can wash up hazardous materials, including chemicals from industrial sites, leading to long-term health risks for affected populations. Floods can cause extensive damage to residential buildings, commercial properties, and public infrastructure. The force of moving water can destroy foundations, collapse walls, and tear apart structures. In many cases, entire communities are submerged, resulting in the loss of homes, businesses, and public amenities like schools, hospitals, and government buildings. This destruction creates an immediate need for emergency shelter, housing reconstruction, and infrastructure repair. Transportation networks, including roads, bridges, railways, and airports, are particularly vulnerable to flooding. Floodwaters can wash away bridges, erode roads, and disrupt railway lines, cutting off access to vital services and delaying emergency response efforts. The destruction of transport infrastructure also affects economic activities, hindering the movement of goods and people, and disrupting supply chains, leading to shortages of essential commodities. Floods can severely impact utilities such as water supply, electricity, and communication networks. Water treatment facilities may be damaged or contaminated, resulting in shortages of clean drinking water. Flooding can also damage power lines and substations, leading to extended power outages that affect both urban and rural communities. Communication networks, including telephone lines and internet infrastructure, are often disrupted, making it difficult for affected populations to communicate with emergency responders and loved ones. Floods can devastate agriculture by submerging fields, destroying crops, and washing away soil nutrients. In many developing countries, where agriculture forms the backbone of the economy, floods can cause widespread food shortages, increase food prices, and lead to economic instability. The loss of livestock, damaged farm equipment, and ruined irrigation systems further compound the economic losses faced by farming communities. Floods can also affect local businesses by damaging commercial properties, inventory, and machinery. Small businesses, which often lack the financial reserves to recover from such disasters, are particularly vulnerable. The disruption to daily business operations can result in job losses, reduced income, and increased poverty, particularly in areas that are already economically marginalized. At a national level, floods can place a severe strain on economies. The cost of emergency response, rebuilding infrastructure, and providing relief to affected populations can significantly impact government budgets. Additionally, the loss of productivity, damage to trade routes, and decline in tourism can further reduce national income. In some cases, the economic fallout from floods can lead to long-term recession or stunted economic growth. Floodwaters can cause severe soil erosion, stripping away fertile topsoil essential for agriculture. The force of moving water can also destabilize riverbanks, leading to landslides and further erosion. Soil degradation reduces land productivity, complicates future agricultural activities, and may lead to desertification in extreme cases. Floods can carry pollutants such as chemicals, pesticides, and sewage into rivers, lakes, and oceans, contaminating water supplies and aquatic habitats. This pollution can have devastating effects on local wildlife, leading to the death of fish and other aquatic organisms, and disrupting food chains. Floods also destroy natural habitats, such as wetlands and forests, that are crucial for biodiversity and serve as natural buffers against future floods. The sudden influx of water can alter the natural balance of ecosystems, affecting species composition and disrupting established ecological processes. Some species may thrive, while others may be pushed to the brink of extinction due to habitat loss or changes in food availability. This disruption can have cascading effects on the environment, ultimately affecting human populations that depend on these ecosystems for their livelihoods and well-being. Floods can also have a profound impact on cultural heritage, washing away historical landmarks, artifacts, and traditions that are integral to a community's identity. The loss of cultural sites, such as temples, churches, monuments, and traditional marketplaces, can erode a community's sense of belonging and continuity, making recovery even more challenging. Floods often disproportionately affect the most vulnerable members of society, including low-income families, the elderly, children, and people with disabilities. These groups are less likely to have access to resources that help them prepare for, respond to, and recover from floods. As a result, floods can exacerbate existing social inequalities, creating a cycle of poverty and vulnerability that persists long after the waters have receded. While the immediate impact of floods is often devastating, they also present opportunities for communities to come together and build resilience. Recovery efforts often involve rebuilding not only physical infrastructure but also social bonds and community networks. The process of recovery can strengthen community ties, foster a sense of shared purpose, and lead to innovative solutions that reduce vulnerability to future floods. Despite the devastating impacts of floods, advances in technology and science have made it increasingly possible to predict and prepare for these events. Effective flood forecasting and early warning systems are critical tools for reducing flood-related losses and enhancing community resilience. This chapter examines the technologies, methods, and strategies used to predict floods and the challenges involved in providing timely and accurate warnings. At the heart of flood forecasting is hydrological modeling, which uses mathematical representations of water movement through the environment to predict the likelihood, timing, and severity of floods. These models take into account various factors such as rainfall, snowmelt, river flow rates, and soil moisture levels. Hydrological models are essential for simulating different flood scenarios and understanding how water will behave in a given region under various conditions. Meteorological data, including rainfall measurements, weather patterns, and temperature readings, are crucial for accurate flood forecasting. Remote sensing technologies, such as satellites and radar, provide real-time data on rainfall intensity, cloud cover, and atmospheric conditions. This data helps meteorologists and hydrologists predict where and when heavy rains might occur, allowing for more precise flood forecasts. Flood forecasting relies heavily on real-time data collection from a network of sensors and monitoring stations. These stations measure river levels, rainfall, soil moisture, and other key indicators to provide up-to-the-minute information on changing conditions. Data from these monitoring systems is fed into computer models, which continuously update flood predictions based on the latest information. An effective early warning system for floods consists of four main components: risk knowledge, monitoring and forecasting, communication, and response capabilities. Risk knowledge involves understanding the flood risk specific to a particular region, including historical data, geographic vulnerabilities, and population density. Monitoring and forecasting require the integration of data from various sources, while communication ensures that warnings reach the right people at the right time. Finally, response capabilities involve having plans and resources in place to take appropriate action once a warning is issued. Timely and effective communication is crucial for saving lives during a flood event. Traditional communication methods, such as radio and television broadcasts, are still widely used, but new technologies, including social media, mobile apps, and text messaging systems, are increasingly important. These tools allow for rapid dissemination of warnings to a large number of people, including those in remote or hard-to-reach areas. However, challenges remain in ensuring that warnings are accessible to all, particularly marginalized communities that may lack access to modern communication technologies. Community-based early warning systems focus on engaging local populations in the process of flood preparedness and response. This approach emphasizes local knowledge, education, and participation, empowering communities to take proactive steps to reduce flood risks. Training programs, drills, and workshops can help communities understand the warning signs of a flood, know what actions to take when a warning is issued, and work together to develop community-specific plans for evacuation and response. Machine learning and artificial intelligence, AI, are revolutionizing flood forecasting by improving the accuracy and speed of predictions. AI algorithms can analyze vast amounts of data from multiple sources, identify patterns, and make real-time predictions with greater precision than traditional methods. Machine learning models can also learn from past flood events, enhancing their ability to forecast future floods under similar conditions. The Internet of Things, IoT, and smart sensor networks are playing an increasingly important role in flood prediction. IoT devices can collect and transmit data from remote locations, providing real-time information on water levels, rainfall, and other critical indicators. Smart sensors, equipped with advanced data processing capabilities, can analyze this data on site, reducing the time it takes to detect changes and issue warnings. Cloud computing and big data analytics are enabling more sophisticated flood forecasting models that can process large datasets quickly and efficiently. Cloud-based platforms allow for the integration of data from various sources, including weather stations, satellites, and social media, into a single, comprehensive model. Big data analytics tools can then analyze this data to identify trends, correlations, and anomalies, providing valuable insights for flood prediction and management. Despite technological advancements, data gaps and uncertainties remain significant challenges in flood forecasting. In many regions, particularly in developing countries, there is a lack of reliable and high-resolution data on hydrological and meteorological variables. Incomplete or inaccurate data can lead to errors in predictions, resulting in either false alarms or missed warnings. Addressing these data gaps requires investment in monitoring infrastructure, data sharing agreements, and capacity building. Not all communities have access to the advanced technologies required for effective flood forecasting and early warning systems. In remote or underserved areas, the lack of infrastructure, electricity, internet connectivity, and technical expertise can limit the effectiveness of these systems. Bridging the digital divide is essential to ensure that all communities benefit from technological advancements in flood prediction. Even the most accurate flood forecasts and warnings are only effective if people respond appropriately. Human factors, such as risk perception, trust in authorities, and cultural beliefs, can influence how people react to flood warnings. Public education campaigns, community engagement, and trust-building measures are necessary to ensure that people understand the risks, believe the warnings, and know what actions to take in response. To enhance flood preparedness and resilience, it is essential to integrate scientific and technological advancements with local knowledge and community-based approaches. This holistic approach ensures that flood forecasting and early warning systems are not only technically sound but also culturally appropriate and widely accessible. Floods are a global challenge that requires international cooperation and collaboration. Sharing data, technology, and best practices across borders can improve flood forecasting and early warning systems worldwide. Collaborative efforts, such as joint research initiatives, capacity-building programs, and cross-border disaster management plans, can help mitigate the impacts of floods and build resilience in vulnerable communities. Addressing the root causes of flooding, including climate change and unsustainable land use practices, is crucial for reducing future risks. Promoting sustainable development, protecting natural flood buffers like wetlands and forests, and implementing climate adaptation measures can help reduce the frequency and severity of floods. By taking a proactive approach to flood management, communities can protect lives, preserve livelihoods, and build a safer, more resilient future. Preparation is key to surviving a flood. Communities and individuals must take proactive steps to minimize risks and protect lives and property. This begins with developing a flood emergency plan that includes evacuation routes, emergency contacts, and a checklist of essential supplies such as food, water, medication, and important documents. Communities should invest in flood defenses, such as building levees, dams, and flood barriers, and maintaining natural defenses like wetlands and forests. Regular drills and public education programs can help ensure that people know how to respond when a flood warning is issued. Raising homes on stilts, waterproofing basements, and creating emergency supply kits are additional individual-level preparations. During a flood, the primary focus should be on safety. Following evacuation orders, seeking higher ground, and avoiding floodwaters are critical steps to ensure survival. It's essential to avoid walking or driving through flooded areas, as even a few inches of water can be dangerous and potentially life-threatening. Floodwaters are often contaminated with chemicals, debris, and sewage, posing additional health risks. After the floodwaters recede, the recovery process begins. This phase is often lengthy and complex, involving cleanup, repairs, and rebuilding. Restoring basic services like electricity, water supply, and healthcare is crucial for returning to normalcy. Mental health support is also important, as the trauma of surviving a flood can have lasting psychological effects. Community resilience, supported by government aid and international assistance, is vital to recovering and rebuilding in the aftermath of a flood.